Good afternoon, everyone. Thank you for joining myself. I am Mr. Ish, and I will be talking about a topic that I have alluded to over the last several videos, but one which I have eluded from. But this topic is going to be implicit differentiation, and we finally get down to it. You know, up till now, when it has come to differentiation and derivatives, even functions, I've always presented those types of functions or equations where one variable was explicitly represented in terms of another. This is what I mean. I've always presented you questions and examples where one variable was explicitly represented in terms of another, where y was equal to something and you had your equation over here, and then we've done the derivative examples based on that. But there are some equations or functions out there where you cannot explicitly represent one variable clearly and cleanly with regards to the other, but rather the relationship between the x and the y, or the two variables, is implicit. You have to express them in an implicit manner with regards to their combined relationship. What I mean by all of this is this. The explicitly presented equations have always been in the form y is equal to this. For example, if I gave an equation x squared y plus y squared was equal to 1, if I wanted to write this explicitly where y was equal to in this format, it would be very difficult. Think about it. The first logical obvious step you would take would be try to isolate y so that you could make it into this form, isolating y. But look at it, if you try to isolate y, you have a power here of 1, here you have a power of 2. It's nearly impossible to isolate it unless you have some sort of algebra software program which can do the isolation and come up with some sort of equation. But however, look at this type of equation. If I had something which looked like this, 2y plus xy is equal to 1, and I want to put this in this form where I'm explicitly representing y with regards to x, you can do it. Watch. When you isolate y, you get 2 plus x is equal to 1, and in the last step you can say y is equal to 1 over 2 plus x, and you can explicitly represent y in terms of x, and you can do it. But however, in this example over, I couldn't do it because you had an implicit relationship between the x and y. Here you have an explicit relationship between x and y. You can clearly and cleanly represent y in terms of x, and then you can go on and differentiate this. And these are the types of questions I've given you in terms of that explicit representation. The whole concept of implicit differentiation is this. When you have questions like this where you have an implicit relationship between the two variables, whatever they may be, I always like to see the x and the y's. You can still do the differentiation techniques using implicit differentiation. Take a look at this. You have an equation which looks something like this. And let's say 2xy minus 5y is equal to 2, and then you have an equation which looks like this. Y square x minus 2 root y is equal to 2, and you have to see which one can you explicitly represent in terms of the other one. You can easily represent this in terms of the other variable. Look, if you were to solve this first equation over here, you would isolate y. You get y into 2x minus 5 is equal to 2, and y is equal to 2 over 2x minus 5, and you can do explicit differentiation of this. You can do explicit differentiation. Over here you have a problem because y has a square over here and y has a power of 1 or 2. It's very difficult to explicitly differentiate this because you cannot get to that step, let alone create a procedure which looks like something like this, an explicit representation of y in terms of x. You just cannot do it. So you have to end up using implicit differentiation technique, which I've kind of hinted towards in some of my examples where you do the derivative of all of this. The point between explicit differentiation and implicit differentiation is this. They both lead to the same eventual outcome. The only difference between them is the procedure that is involved. I want to present an example where I'm going to present a function which can be explicitly represented in terms of one variable with regards to the other, and I'll show you that the implicit and explicit differentiation will lead to the same outcome for both of those before we start getting into the whole process of implicit differentiation. I want to show you just how implicit differentiation and explicit differentiation are apparently different, but the outcome is always the same. Now watch, I've already given you the introduction of this video where I stated that for some variables, for some functions and equations, the one variable can be explicitly represented in terms of the other, where y can very cleanly represent your equation and there's some equations out there where you cannot express them explicitly because of the implicit relationship between the two variables, and you have to keep your equation as is and you do the implicit differentiation. If you were to take the route of explicit differentiation over here, which you can, because you can easily isolate y, look what happens. When you isolate y, you get a 2x minus 4 is equal to x, and when you solve for y, you get x over 2x minus 4. Now these are the type of questions I've given you all along in terms of derivative, and you want to find the derivative of this. You're doing explicit differentiation over here. Explicit differentiation. When you do the explicit differentiation, you have to do the quotient rule over here. Here's my f function, here's my g function. It's a g function multiplied by the derivative of the f function minus the f function multiplied by the derivative of the g function, right, over the g function squared. Now look, when we simplify this, what do we get? 2x minus 4 times the derivative of x is just a 2x minus 4. X times the derivative of 2x minus 4 is a 2x minus 2x over 2x minus 4 whole square. Now look, when you simplify this, what's your derivative? It's minus 4 divided by 2x minus 4 whole square. That's your derivative. Now imagine you had this point on your curve. Let's call it 1. In place of x, you put 1. You get 1 divided by 2 minus 4. You get a minus 1 over 2. Alright, if supposedly you have this point on your curve and this is my x value, you put your x value over here. What do you get as your instantaneous rate of change or your slope of the tangent line? You do minus 4 divided by 2 minus 4 whole square. Because I'm plugging in this x value in place of x, what do we get? You get a minus 4 over minus 2 square is a 4, you get a minus 1. So with regards to the explicit differentiation, I'm getting an instantaneous rate of change of minus 1. Now I want to redo this whole question using implicit differentiation and using the same coordinate, and I should still get a minus 1, and I want to show you that. So when we're doing implicit differentiation, assuming you didn't isolate y, or you couldn't isolate and you couldn't represent cleanly one variable fully in regards to the other, where you couldn't clearly say y was equal to your something, and you couldn't do that, then you do implicit differentiation where you just differentiate the entire equation together. And this is something I've shown you, but I've never formally shown you, because I've shown you some examples of this, but I've never clearly talked about it. So let me start this video by doing that. You would take the derivative of all of this. You take your 2, you'd isolate it out, and then you'd have to do the derivative of this xy component. You do the derivative of this 4y component, and you do the derivative of the x component. And I'll show you a bit of the technique over here, though in the rest of the video I'll be showing you the technique again more clearly. But anyhow, you have the f function, the g function, you have a product function. You'd multiply y by the derivative, just like the product rule, of x plus x multiplied by the derivative of the y function. And the procedure for that is d over dy, your y variable, and then dy over dx. These two always come together. Minus, take the 4 out, the coefficient out, derivative with respect to y of that y, and dy over dx. And in these questions you're always solving for dy over dx is equal to d over dx of x. Derivative of x is just a 1. Now you basically have to just do the derivative across. Look, y multiplies by the derivative of x, which is just a 1, you just get a y over here. X multiplies by the derivative of y, which is just a 1, but this x stays retained to this dy over dx, because you have to solve for dy over dx. Look over here, minus 4 will multiply by the derivative of y, which is just a 1, but this 1 will stay attached to this dy over dx is equal to 1. Now open this part over here, you get a 2y plus 2x dy dx minus 4 dy over dx. And remember, you're always solving for dy over dx is equal to 1. You can take this 2y on the other side. Let's do that. Let's take the 2y on the other side. Watch what happens. You get 1 minus 2y. I've done nothing fancy over here. I've just taken the 2y on the other side. Isolate dy over dx. Isolate dy over dx. It goes in this 2x times. It goes in this minus 4 times. And it was equal to 1 minus 2y. Solve for dy over dx, which is what you're doing, the implicit differentiation, which is the same thing as y prime. I've shown you that in the previous video. You get 1 minus 2y over 2x minus 4. You see, in the implicit differentiation you have an answer which has both variables, x and y. Whereas in the explicit differentiation, you had no y because you clearly represented your equation in this form. In implicit differentiation, all your variables may show up in your derivative, but that's fine. You just take these x and y values and you plug them in there. Here's my x value, here's my y value, minus 1 over 2, and you plug it in and see what you get. You do 1 minus 2 times minus 1 over 2, which is your y value, divided by 2 times your x value, minus 4. Solve this out, and what do you get? Here on the top, you'll get 1 plus 2 times minus 1 over 2 is a 1. 1 plus 1 is a 2 over 2 minus 4 is a minus 2. And what are you getting? A minus 1. Look over here. The slope over here, instantaneous rate of change of your tangent line was a minus 1 using explicit differentiation. And the same slope, which represents the slope of the tangent line or the instantaneous rate of change using the implicit differentiation is a minus 1. So we know over here our instantaneous rate of change using both methods is equal to a minus 1. This in conjunction with this can give you your equation of your tangent line. The point I'm making is both implicit and explicit differentiation provide you the same eventual outcome. The only difference lies in the procedure whereabout how you arrive at that outcome. In explicit differentiation, the process is much quicker and it's easier, but there are some instances where you cannot clearly express one variable in terms of another, and you have to, or by no other option, you have to do implicit differentiation. Here I could have done explicit differentiation, but I only chose to do implicit differentiation as well for the sake of the example. And I've shown you at the very start of this video the types of functions where you may not be able to explicitly differentiate, where you cannot cleanly represent one variable with regards to the other, and those are the types of functions where, like for instance, your y values have different orders. Imagine this: root y minus xy is equal to 2, and you have to solve for y, and you couldn't do it because look over here, y here has a degree of a 1 over 2, here y is a power of 1, and it's very difficult to isolate y and represent a clean explicit answer. You just cannot do it. So it is in these type of instances, and you can have trigonometric, exponential, logarithmic, whatever functions involved, and you just cannot cleanly express your variable explicitly with regards to the other, then you have to do implicit differentiation. But keep in mind, the results of both differentiation techniques are always the same. It's just one process is more involved than the other, but they both give you the same final outcome. Stay tuned for more explicit explanations with regards to implicit differentiation now in the remainder of this video. Remember, when we have a function which is explicitly stated in one variable with regards to another, we use a technique of explicit differentiation, and you get like a derivative over here as your answer. When you plug in this derivative, your x coordinate, you get your slope of the tangent line. That's how the process works with explicit differentiation. When you have a function over here or an equation, let's just say a function or an equation where you cannot explicitly represent the one variable cleanly with regards to the other. Now remember, here's the difference. You have to use implicit differentiation. When you use implicit differentiation, you get a different kind of derivative. And the difference is this: in this derivative you'll have to put x and y values to actually arrive at the slope of your tangent line. So that's a clean difference between the two processes. The explicit differentiation is usually with regards to your derivative one step closer to your actual slope of the tangent line. When you're using implicit differentiation, you're still kind of one step behind because the other step is consumed by the application of the y coordinate in addition to the x coordinate, which you have to do any ways up over here. So that's how this is one step behind, but you still arrive at the same final outcome. So with this framework in mind, let's look at an example in terms of its technique on how we do the process of implicit differentiation. Very quickly over here on the bottom, I'm going to show you how we do the technique of implicit differentiation just with regards to how your notations will arrive. When you're looking at any variable or any part of an equation or a function which has somehow the x variable in it, you're always doing derivative with regards to x, and you just take this forward. Anytime you have a y variable kick in, right? A y, and it's a turn for the y variable to be affected, your notation is you're doing derivative with respect to y of that variable, and then dy over dx, and this is what you're solving for in your implicit differentiation. And a real good example to look at very quickly over here on the bottom is right here. If you're looking at something which looks like xy and you have to do the derivative of xy, you know this is a product of two functions or two variables x and y, you can look at it very clearly over here. Imagine if you have to do this, this is your f function, your g function, you do your g function multiplied by the derivative of the f function plus the f function multiplied by now the derivative. See, now when the term for the y variable has come up, you have to follow this scheme over here. You'll do d over dy, y, dy over dx, and that's how your notation will play out. When you actually go to the step over here, alright, when you actually go to the step, the d over dx will, the x derivative will be applied because you're doing the derivative of x, and it'll be consumed because the derivative of x is just a 1, you end up with a y over here. And here the x will multiply by the derivative of y, the y will be consumed because the derivative of y is just a 1. But when you consume that y variable, you still keep this variable right here, dy over dx, attached to it. And when I show you examples, keep this in mind. This dy over dx is very important. The whole dy over dx, which is kind of synonymous with this, you have to keep this aspect right in mind, because when you're doing an implicit differentiation, you're solving for this in the end, and you're taking everything on the other side, just like I'm showing you over here, and just like I will show you in these following examples. So your task is for this equation, which cannot be explicitly represented, where you can say y is equal to something, you cannot explicitly represent one variable with regards to the other. Your only option here is to use implicit differentiation, and this is how the technique is, and you might have already picked up on it. You start out by saying that you're going to differentiate this entire equation, and then you separate it out. Some of these steps you can do exactly in your head. I'm only doing them over here for the purposes of video, and you know, with time and practice, things become automatic and things become shortcut. Now look over here, you can still write over here d over dx y squared, you can still do that, and the derivative of 4. But now when you actually go into the proper layout, implicit differentiation layout, look how I'm going to rewrite this. I'm changing nothing over here, but here I have a product rule which will kick in. So you'll have your f function and your g function. It'll be the g function multiplied by the derivative of the x function, which is the f function over here, and the f function here, I keep confusing x and f. Anyhow, multiplied now by the derivative of y. You see how the dy and dx is kicked in? I have a d over dy and then dy over dx. Now look where I'm over here, minus derivative of y and then dy over dx. You're always solving for these dy over dx is equal to the derivative of a constant is 4. Now look over here, we have to always keep our eyes on these items over here, because this is what we have to solve for. In the next step, you actually do the derivative of what you can. Derivative of x squared is a 2x, and you've lost this d over dx. When you do the derivative, you lose that label, the derivative label. Now look where the derivative of x is just a 1. It attaches with this y, the 1y, and you lose the derivative label. Now look over here, x multiplied by the derivative of y. The derivative of y is just a 1. This label over here, d over dy, is lost, but this label dy over dx, now I'm saying the word label over here. The label dy over dx is not lost. You keep that. The derivative of y squared is a 2y. This initial d over dy label is used up by the process or the procedure of derivative, but the dy over dx label is still kept. Now look over here. You have to isolate and solve for the dy over dx. Take everything on the other side and keep what you have attached to these labels over here. I'm going to do some steps over here. Dy over dx. I'm isolating this from these two. You get x minus 2y. Remember, this right here is just the algebra part. You take these two on the other side, you get y minus 2x. Now you actually solve for dy over dx, which actually represents your implicit differentiation outcome. And you take this on the other side, you get y minus 2x divided by x minus 2y. And this right here is your implicitly derived derivative. And now if you actually had an x comma y value, a coordinate set, you'd plug them here in place of y's and x's, and you'd get your slope of your tangent line, the instantaneous rate of change. So this is how the fundamental difference is between implicit and explicit differentiation. And do not be comfortable in the fact that implicit differentiation is only involved with polynomial expressions. You can use them for any kind of expression. Functions, trigonometric, logarithmic, anything. You can apply them anywhere. But this right here was an example which shows you the technique. You have to pay very close attention to these labels d over dy and then dy over dx. And you got your y variable in here in between. When you do the derivative of y, this label is removed, but this label right over here stays. So remember, when we're looking at questions like this, our goal is to do implicit differentiation, and we have the goal in this video to learn the technique of this implicit differentiation. And once you learn the basic technique, it's just a short matter of you applying that technique to a variety of equations. And if you were to try to explicitly represent this function in terms of y was equal to something, you couldn't, because y's are too inherently embedded that you couldn't isolate them cleanly. And then at the end of this whole process, you'd have an x comma y value. You'd plug it into your derivative, and you'd get your instantaneous rate of change or your slope of your tangent line. But let's look at this process. The process starts like this. Then you separate it out. Derivative of sine xy plus d over dx, you can do 2y squared, is equal to the derivative of this constant. And now you have to start doing your technique application. Look over here. You have a composite function. If u is equal to xy, then f of u is equal to sine u. And within this, you will have the product rule kicking into play. So let's watch and let's play this out. Derivative of u sine u. And then derivative with respect to that variable which it's representing, you have xy over here, plus look over here, derivative y d or dy, 2y squared dy dx is equal to 0. You can bring this 2 right out over here, and that's fine. Separate the coefficient from the variable. Now we have to come over here and start solving. D over du sine u, and we have to do the product rule over here. You have the g function multiplying by the derivative of the f function, and adding to the f function multiplying by now the derivative of the g function. And you see how I'm bringing these extra labels into place, plus 2 times the derivative of the y squared dy dx is equal to 0. Now in this next step we have to actually do some real work. Sine u, derivative becomes cosine u. Y times the derivative of x is just a y. X times the derivative of y is just an x, because the derivative of y is just a 1. But don't forget the label that it comes with, dy dx. Now look over here. The derivative of y squared is a 2y. 2 multiplies with this 2, you get a 4y. But don't forget this dy dx label, because you have to solve for that. Now in the next step, it makes sense to actually open this up. You get cosine u, and let's bring the y before it, plus x cosine u, and I'm going to keep the dy dx with it, plus 4y dy over dx is equal to 0. So you can see how this process is a little bit more cumbersome, but it actually works. We bring space creation over here. We make space. Now look over here. We have to isolate for this dy dx and take everything on the other side. These are my dy over dx terms. I isolate them dy over dx, and you isolate x cosine u, we can substitute for the u at the very end, plus 4y is equal to, you take this y cosine u on the other side, you get a minus y cosine u. Now I'm going to solve for dy dx, and I'll take this item onto the other side. You get a minus y cosine u over all of this, x cosine u plus 4y. Now in the final term, you know, dy dx is synonymous with this y prime, meaning the implicit differentiation with regards to the y, you just plug in the u. You know the u was equal to xy. Our variable substitution here, u was equal to xy. Now look, minus y cosine xy over x cosine xy plus 4y. Now look over here, the very distinct difference between implicitly derived derivatives and explicitly derived derivatives is this. In explicitly derived derivatives, you'll only see a single variable in your derivative. And since I'm talking about x's and y's, you'll only see the x's in your explicit derivatives. In your implicitly derived derivatives, you see both x's and y's. What does that mean? It means this. You'll have to put x and y value of the coordinates in those places of x's and y's to derive at your final slope of the tangent line. Alright? you'll have to put your x and y coordinates both, and then only you'll get your slope of your tangent line. So you can see how vastly different this process is, and we'll continue to look at a few more examples. Let me show you this question by changing gears just a little bit, and I'll show you the derivative of this in both ways. And I'm going to show you how the implicit differentiation kind of mirrors the explicit differentiation. Now look over here. If I were to solve explicitly for y, I could. You'd have y squared is equal to 25 minus x squared, and then you'd say y is equal to square root of 25 minus x squared. Here you've explicitly stated what y is in terms of x. It is square root of 25 minus x squared, and you're explicit about it, and it's good. And let's keep this value expression over here and put it aside. Now let's look only at explicit differentiation, and let's look at this. Let's do a derivative of this explicitly. Derivative and root u and derivative with regards to x, 25 minus x squared. What do you get? When you do the derivative of this, you get 1 over 2 root u, and when you do the derivative of this, you get a minus 2x, minus 2x. These 2's will cancel out. What you end up getting is a minus x over square root of the resubstituted u value, 25 minus x squared. Now let's put this value and let's circle it, and we'll come back to it. Now let's do the implicit differentiation over here. D over dx implicit differentiation, x squared plus y squared is equal to 25. So let's in this next step get right down to it. The derivative of x squared, and we're going to do d over dx x squared plus, we'll write this in the proper form, dy dx, and the derivative of a constant, which will be handled in the next step. Look over here, everything is laid out in the proper form. Now let's get down to the actual derivatives. X squared becomes a 2x, y squared becomes a 2y, but the label gets retained with it, and the derivative of this constant is just a 0. Now look what's going to happen. I'm going to solve for dy dx. 2y dy over dx is equal to minus 2x. You take the 2x on the other side. You can cancel these 2's out because they'll cancel out in a divide. It'll become minus 2 divided by 2. They'll cancel out. You have a y dy dx is equal to minus x. Therefore dy over dx is equal to minus x over y. Minus x over y. But look over here. What did y initially represent? Y represented this, right? And if you resubstitute that y in place of this, you get minus x over square root of 25 minus x squared, which is your implicitly derived derivative, which mirrors your explicitly derived derivative. And we will look at a few more examples, and that'll be the end of it for this video. In this interesting question, we have to differentiate and come up with a derivative for this. You can call it a function. If you look at it, you have x and y coordinates, or x and y variables over here, which are so intricately combined that it would be difficult to separate. Or even if you could explicitly separate, it would make sense just to continue with this in an implicit manner. And you can do that because you know implicit differentiation is not that hard. You have a function here in the product formation. You're going to use a product rule over here. You'll look at the f and then the g function, and you'll proceed with that. The g function, and these are inverse trigonometric functions over here, multiplied by the derivative of the f function, which we will see. And you know we've done derivatives of inverse trigonometrics, nothing hard about that. The f function now multiplying, which will be over here the eventual derivative of this g function, and you know the derivative of 1 is just a 0. So this is the scheme over here we have to proceed with. It shouldn't be too hard. Look over here. When we're doing the derivative over here with regards to y over here, we're going to have to bring in our special labels. Let's start bringing in the derivatives as we go along now. You know over here what we would really have put over here would have been a derivative with regards to y, and then we would have done a dy over dx is equal to the derivative of 1, which is a 0. The labels we have to be very wary of, and we're always solving for dy over dx. And you know the derivatives of inverse tan is 1 over 1 plus x squared, and the derivative of inverse cotan is minus 1 over 1 plus x squared. So what's the derivative of inverse cotangent in regards to x? It would be minus 1 over 1 plus x squared. You know that from our derivative of inverse trigonometric functions video. And you have the derivative over here playing out with regards to y. Remember implicit differentiation at play. This d or dy will be consumed with the arrival at the derivative of inverse tangent. You see how I'm bringing a y square over here because we're dealing with the y variable, and you still have to keep that label attached, is equal to 0. And you know we're always solving for dy over dx, always. Take all of this onto the other side, but look over here. This minus 1 over 1 plus x squared is the same thing as saying minus over here. When you take this minus on the other side, it becomes a positive. Look over here. Cotangent minus 1 over 1 plus y squared dy over dx is, I'm looking at over here, is equal to this expression aspect on the other side as a positive, tan minus 1 y times 1 over 1 plus x squared, same thing as saying over 1 plus x squared, over 1 plus x squared. You see how everything's all playing out and it's beginning to take form over here. Nothing too outstandingly difficult over here at all. We're solving for dy over dx, and you know this 1 plus y squared is the same thing as saying this over 1 plus y squared, because these are in a product relationship. You have the numerator, you have the denominator. Let's solve for dy over dx. You're basically going to take this fraction on the other side and it's going to go in a divide, and we'll write that out. Tan inverse with regards to x over 1 plus x squared all over this. You basically have inverse cotangent over 1 plus y squared. And I'm making a little a silly mistake over here. You see I have inverse tangent y, I have inverse tangent y. Slowly my y's creeped up and began to look like x's. So this right here is still a y over here. And we're still solving for this. Now you have to flip this around. Let's flip it around. You get inverse tangent minus 1 with regards to that y. And sometimes the handwriting can be the worst thing over here. Your own handwriting can fool you and you can end up making a mistake. You flip this around and you get a 1 plus y squared over inverse cotangent minus 1 x. And you could say this right as your final answer and you would be good. And this right here is the derivative of this expression over here. If you were to plug in the x and y coordinate, if you had those, you could get the instantaneous rate of change for this expression over here. So we have another interesting question over here. Cosine x plus y equals 2y. We have a trigonometric identity over here, what looks like 1. The sum formula for the cosine, and you know cosine x plus y in terms of the identity equals cosine x, cosine y, minus sine x, sine y. And you would think that maybe we should proceed by the substitution of this expression over here, so we would open it up. But I would recommend against that, because you're going to unnecessarily complicate this implicit differentiation question. Because look at these, you have xy, you're just unnecessarily going to make it complex. The way I would proceed over here is by means of a substitution using the chain rule, and you wouldn't end up with a complex expression. Look over here, if u is equal to x plus y, then we have f of u is equal to cosine u. Look over here, we have a single y and we have no x or y over here, but look over here, we have xy. Substituting this is better over here than substituting that entire identity. I wouldn't do the identity way, and we would proceed with the chain rule over here. Derivative with regards to x. That's how I would proceed over here. And sometimes it's smart to proceed in that way versus using a trigonometric identity. Look over here, derivative with regards to u, you'll have cosine u, and look over here, du or dx, we'll have x plus y over here is equal to d over dy, and I can bring the 2 before, coefficient can be brought before y, dy over dx. Our only main challenge is this part right here, otherwise we would have had a lot of main challenges. Product rule here, product rule over here would have been just a mess. Now look over here, d over du cosine u. Now we'll do simple differentiation rule, d over dx of x plus d over dy y, dy over dx is equal to 2 multiplying by the derivative of y, which is just a 1, which will stay retained with the dy dx. Now you only have to worry about this part, and each of these will individually multiply with cosine u, but it's not hard. The derivative of cosine u is a minus sine u. The derivative of x is just a 1, and the derivative of y, dy dx, is just a dy dx. And you know you have this equaling to 2 dy dx. When you open this up, then you have to start isolating the dy dx terms. Look over here, you get minus sine u dy dx is equal to 2 dy dx. you have to just bring the dy dx terms together. I'll just take this on the other side. I'll get a minus sine u over here is equal to 2 dy dx plus sine u dy dx. And you're seeing this is just a simple algebra over here. Now isolate for dy dx and solve. And let's take this to completion. Dy over dx, which is the same thing as saying the derivative of y, derivative of this expression implicitly derived with regards to y is equal to minus sine u, what was u? X plus y, let's resubstitute x plus y over 2 plus sine u, which is x plus y, right? And right there we're seeing it come into play over there, and you're done. Or you can say the other answer, sine x plus y over minus 2 minus sine x plus y. I think this right here is a better answer. You have a better presentation over there. Better answer. And that right there is your implicitly derived derivative of this expression with regards to y. And you would roll with that. Minus sine x plus y divided by 2 plus sine x plus y, and you're done. How about this question over here? We have x squared cosine y plus sine of 2y is equal to xy. You know, if you want to explicitly separate the y and have a y equals a function explicitly and then proceed with explicit derivation, that's going to be very difficult. Implicit derivatives and implicit differentiation is the way for this question as well, because the x's and y's are just too inherently bound together that separating them is just going to be a very difficult task. So when you know the technique of implicit differentiation, you might as well use it. And we're going to do that. You know, you have the product rule which is going to apply over here, you'll have the chain rule apply over here, and you have a product rule applying over here. So we have a whole lot of action going on over here. And let's start working over here. Cosine y, this is my f function, g function, chain rule, f function and g function, times the derivative of x squared plus derivative of x squared, which is my f function, multiplying by the derivative of cosine y dy dx, plus, now we're going to bring in the chain rule. We know the chain rule, we can do it in our head. If u is equal to 2y, f of u is equal to sine u. D over du sine u, du over dy. See, du over dy, 2y, and then dy over dx, because we have a y involved over here, is equal to, now we have to do this part right here, the product rule over here. Y multiplying by the derivative of x plus x multiplying by the derivative of y, and then dy over dx. Look at all these dy dx terms we have. One over here, one over here, one over here, and then we have to marry all of these together and solve for these. Those will be all solved. Now let's start solving this out. Cosine y multiplied by the derivative of x squared is a 2x, plus x squared multiplied by the derivative of cosine y is a minus sine y dy dx, plus derivative of sine u is a cosine u. Derivative of 2y is just a 2. And then we have the dy dx attached with that. Let's not forget that. Y times the derivative of x is just a y. Plus x times the derivative of y is an x dy dx. Here's my one dy dx, here's my other, here's my other. We have to bring them together somehow. So let's start working over here. I'm going to rewrite this. I'm going to bring the minus over here. I'm going to bring the coefficients together and you'll see it. You have a cosine y 2x. See this coefficient 2x, I've written it first. 2x cosine y. This minus will affect this positive and make it minus x squared sine y dy dx. 2 will come as a coefficient. 2 cosine u. I'll add all of these u's at the end. Dy dx is equal to y plus x dy dx. Now in this next step over here, I'm going to bring all the dy dx's onto the left side, and I'm going to bring everything else onto the right side. We're going to do this fast. And look over here. We have a dy dx isolating. I'm going to start isolating in my head. This dy dx is attached to a minus x squared sine y. This dy dx is attached to a plus 2 cosine u. When you bring this x dy dx, it would have become a minus x over here. And you have a y over here. And you have this 2x, which will go on the other side. This 2x cosine y is a minus 2x cosine y. So now that we've come all the way up to over here, we just have to finish this question and solve for the actual dy dx, which you know represents this, the implicitly derived derivative with respect to y. You're going to take all of this expression on the other side, because it's multiplying with this, it's going to divide over there. So your final answer is y minus 2x cosine y over, that's your this part right here, divided by all of this. Let's write this as 2 cosine u was this right here, 2y minus x squared sine y minus x. And this right here is your final answer. If you plug in the x and the y values over here, you'll come up with the instantaneous rate of change or the slope of the tangent line at that point x comma y. See, here you have to plug both x and y values to get your instantaneous rate of change. For explicitly derived derivatives, you only plug in the one variable, whether it be x or whether it y, what are you obtaining as your final variable. In these type of implicit derivatives, you have to plug both variables in. When you look at this question over here, and if you are tasked with finding the derivative of this, you might as well just proceed implicitly, because separating everything in terms of y will not be easy and it will not be enjoyable. And since you're getting very comfortable with the technique of implicit differentiation, use it. Look over here. We have a product of two functions, so the product rule will come over here. We just have basic individual components over here, which will easily derive. And we have the f function, the g function. Let's proceed implicitly. We'll have the g function multiplying by what will become the derivative of the f function plus the f function multiplied by what will eventually be the derivative of that g function with its appropriate label. As you can see, everything is being laid out properly. The derivative of this y, d or dy, y, with regards to dy or dx, minus the derivative of 1 is just a 0. You know you're always solving for dy or dx. In all of these, you're always solving for that. Look over here. Derivative of x is 1, so this tan y stays as is. Plus x multiplied by the derivative of tan y will be secant square y with its attached dy dx is equal to derivative of y is just a 1, but it will stay with its label of dy over dx. Isolate the dy over dx. Let's bring this onto the other side and keep the tan y over here. Nothing wrong with doing that. Is equal to dy over dx minus x secant square y dy dx. Isolate the dy dx, which you know is synonymous with this. The implicitly derived derivative of your function with regards to y is going to be equal to the tan y divided by this. When you isolate dy over dx, you're getting a 1 over here. You get a 1 minus x secant square y. And you know this isolation is a technique which is of very much second nature to you all, because you are all good in algebra. Look over here. Here's my final answer. Tan of y divided by 1 minus x secant square y. We can just write it over here again. This derivative, the implicitly derived derivative, is equal to tan y, and you can do 1 minus x secant square y, and you are done. Let's look at this question over here. We have to find the derivative of this. You know we have an exponential function at work over here. It would be difficult to use explicit differentiation because it would be difficult to present an explicitly derived function where y is expressed explicitly in terms of x. It would be difficult. Logically, you want to proceed with this using implicit differentiation. So let's do it. And we have a composite exponential function over here, so we might have to employ the chain rule. And let's proceed. Let's look over here. If u is equal to x squared y, then f of u is equal to e to the u, and we'll proceed with that. Open this up. D over du, e to the u, and then du over dx. You have x squared y is equal to derivative of x plus, you can do derivative in terms of y dy dx, and you know you're always solving for dy over dx. That's the mainstay for these type of questions. Now look over here. We'll do a product rule over here. Derivative with respect to u, e to the u, and we have a product rule kicking over here. The y multiplying by the derivative of the x squared plus the x squared, which will multiply by the derivative of y, and then you have that label which comes with it, is equal to derivative of x is 1 derivative of y is just a 1, but that y stays with its label dy over dx. Let's open up this part over here. Look, e to the u derivative is just e to the u, which will multiply by what's going on over here. X squared, derivative is a 2x, it multiplies with the y. Derivative of y is just a 1, but this x squared will stay attached with that dy dx is equal to 1 plus dy over dx. We have to somehow get the dy over dx together because that's what we're solving for in these cases. Let's open up the parentheses. We'll have 2xy e to the u, we'll substitute for u at the end, plus x squared e to the u dy over dx. I'm going to bring this dy over dx on this side because I want to bring these dy dx's together is equal to 1. Let's take this 2xy e to the u to the other side. It would become a minus 2xy e to the u, and when we've done that we can erase this aspect over here. Let's isolate the dy dx. Dy over dx, you have x squared e to the u minus 1 is equal to 1 minus 2xy e to the u. Now in this next step we're going to solve actually for dy over dx, and we're going to resubstitute. Look, dy over dx, which is the same thing as saying this y prime, it's the same thing as saying that y prime, is equal to 1 minus 2xy e to the u. What was u? Was x squared y over x squared e to the u. X squared e to the u was x squared y minus 1, and that right there is your final answer. So when you have this derivative, and I'm going to write it here again in a more open format, 1 minus 2xy, and I mean like in a more broad or more seeable or legible format, x squared e to the x squared y minus 1. So when you have this derivative over here, all you would have to do is plug in the x and y values, which would give you your slope of your tangent line, and our final answer is right over here. Here is a question right before you, which will be followed by a similar question but slightly more difficult, and this is going to be slightly out of in tune of what we're showing over here. We'll still be using implicit differentiation, but we're not finding the first order derivative, we're finding the second order derivative. We're finding a derivative on top of a derivative, and remember I'm following this question with another similar type of question, and let me show you how we go about doing second order implicit differentiation. You know, you're going to start with the basic way. Separate this out. Derivative x cubed plus derivative, let's just write dy y cubed dy dx is equal to 0. Now writing this should be second nature to you after going through all of these examples. Let's do the derivatives over here. X cubed is a 3x squared, y cubed is a 3y squared dy dx, and you know you're always solving here for dy dx is equal to 0. So dy dx over here, which is your first order derivative, is going to be minus 3x squared. You take the 3x squared on the other side and you divide by 3y squared, and you know the 3's cancel out. What do you get? Minus x squared over y squared. That's your first order derivative. This first order derivative and this part over here must be remembered for the part which will proceed, because we're going to be doing some substitution at the very end. But a second order derivative now will continue from the end result of the first order derivative. Now this has become your function which you have to derive for the second order derivative. So let's do that. Let's bring the minus outside, and we're doing the derivative of this x squared over y squared. We're doing that. Now look over here, we have a quotient rule, f function, g function, and let's proceed with that. Let's keep the minus out the whole time. This minus coefficient, we'll keep it out the whole time. We'll do the g function multiplied by the derivative of the f function minus the f function multiplied by the derivative of the g function over the g function, which is y squared, to the square, which is y to the fourth. Now let's open it up down over here. We still have the minus outside. Y squared times x squared is a 2x y squared. You see the derivative of x squared is a 2x. Now bring that minus over here. Derivative of y squared is a 2y x squared, but look where we have a dy dx. Dy dx is equal to this, which is equal to that minus x squared y squared. You can see substitute minus x squared over y squared. You can do that clean substitution over there. This is all over y to the fourth. You see over here, we substituted this dy dx. Instead of recognizing and continuing with this, we might as well substitute this right over here and continue with that. We can substitute dy over dx the y prime derivative for exactly what it is, and that's what we're doing. Now let's look over here. We're going to open this up. We're going to come over, we'll open it up. We're still keeping the minus outside. 2xy square, this minus and this minus becomes a plus. Now look over here. This y to the first order and this y square will cancel each other out, so you'll have a y in the denominator, and this 2x squared will multiply with x squared to get 2x to the fourth. See, 2x to the fourth over y. And you can see that. That's all algebra. This 2 and this x squared multiplied with this minus x squared, and you became a positive, and you had the 2x to the fourth. But this y to the 1 over here cancel out this y squared and made it just a 1. Y to the power of 1. If you do the common denominator over here on the top, for this top expression, you'll have a y, and 1 goes in y times y multiplies with 2xy squared to give you 2xy cubed. We still have this minus outside, which I'm carrying, plus 2x to the fourth over y to the fourth. If you bring this, you have over y to the fourth. If you bring this y and you combine it with this, you're going to get over y to the 5. Look what you get. You get minus 2xy cubed, let's keep the minus outside, plus 2x to the fourth over y to the 5. That's what we're getting so far. Nothing fancy over here. It's all just algebra playing in. I've done nothing, no magic tricks, none of that. Now look over here in this expression, you can isolate a 2x. I have a 2x here, I have a 2x over here. Let's isolate, and let's keep the minus outside. We're coming over here. You have that minus outside, and I've isolated a 2x. I get a y cubed plus 2x goes in here, x cubed times, because I've isolated the 2x over y to the 5. Now look over here. X cubed plus y cubed was equal to 1, right? Wasn't it? You can take that 1 and you can substitute it down over here. You can actually substitute this 1 because it equals x cubed plus y cubed for right over here to get your final answer, your final second order derivative. And when you put that 1 over here, you can get a minus 2x divided by y to the 5. So why don't I just come over here and I post the answer right here on the top for you to see. When this 1 gets substituted right over here, you are left with a minus 2x over y to the 5, and that's your final second order derivative of this expression over here. And this 1 substituted for this, and you have a minus 2x times 1, which is a minus 2x, divided by what you already have, y to the 5, and that right there is your final answer. We will be following this right here by an exactly similar question, but slightly more harder. Not too much harder, but slightly, and it'll be in exactly the same process. But remember over here, we did 2 substitutions. In addition to the implicit differentiation, we substituted the first order derivative in the second order process where it showed up. We did that. And in the very end, we substituted what the original expression was for what we ended up with having over here by means of isolation, and that took us to our final derivative, which is right here on the top. So keep that in mind, how it's slightly more different when you're doing second order derivatives implicitly, or third order derivatives, it's more involved. As our last question, we want to look at this. You could explicitly solve for y in terms of x, and you could do explicit differentiation, but I want to do this question implicitly. But more than just that, I want to find the second order derivative of this equation over here. You see the 2 lines over here, the 2 primes, it means we're looking for the second order derivative. So we'll proceed by finding the first order derivative. Then that first order derivative answer will be serving as the start of the second order process implicitly in both cases. Now look over here how we proceed. We're going to proceed by doing the derivative of all of this, of x to the fourth plus d over dy, y to the fourth, and then you have that label dy dx is equal to derivative of 16, which is a 0. Now let's do this. X to the fourth is a 4x cubed, y to the fourth is a 4y cubed, and it stays with this dy dx is equal to 0. Now let's just solve for dy over dx algebraically in one step. The 4x cubed is going to come on the other side as a minus 4x cubed, and the 4y cubed is going to divide over here, and what do you end up getting? Minus x cubed over y cubed. And this right here is our first order derivative. So your first order derivative, which is represented as this, or the same as dy over dx, see, the same as this, is equal to minus x cubed over y cubed. Now let's use this and start the procedure for the second order derivative. Now look over here. I'm going to look at this and I'm going to start doing the derivative of this. I'm going to bring the minus outside, which is fine. It serves as a coefficient, and we'll do x cubed over y cubed. This is nothing more than the quotient rule kicking in place, except we have two different variables, but same. We'll have minus, we'll have the g function multiplying by the derivative of the f function minus the f function multiplying by what will be the derivative of the g function, c dy or dx, all of that coming into place, divided by the g function squared, which is y cubed squared, y to the 6th. Now let's come over here. We have this minus at the very beginning, right here, this minus, we're carrying it down. Let's work in this. We have a derivative of x cubed, which is a 3x squared, multiplying by that y cube is attached to. The derivative of y cube is a 3y squared, multiplying by the x cube it's attached to. But let's not forget the dy dx label, which sticks with it, all over y to the 6th. Now look over here. We have the dy or dx label over here. We don't have to start worrying too much about it because we know what it was equal to. The dy or dx was the same thing as the first order derivative, which is the same thing as this. So you can take the same expression and plug it right over there. So you can eliminate the dy or dx entirely and then proceed that way. And let's see what happens. We do minus 3x square y cube minus 3y square x cube multiplied by this minus x cube over y cube, which is your dy over dx, all over y to the 6th. Now we have to do this part over here, the limited space we have, and do this question. Look over, let's keep the minus outside and let's look over here. Look over here, this y square will cancel out with this and we'll make it y to the 1. And you'll see that. And this minus x cube will multiply with this minus 3x cube and you get positive 3x to the 6th. So let's look over here. 3x to the square y cube plus 3x to the 6th over y. This is all over 1 because you can do a common denominator. And this right here is all over y to the 6th. When you do this procedure here on the top, you have 1 going in y times, you can multiply over here. Common denominator, you get 3x square y to the 4 plus 3x to the 6th over, and you can bring the y down and make it y to the 7th. You're seeing all of that. That's just algebra at play. From over here, you can isolate this. You can isolate, let's keep the minus outside. We're coming up over here. You can isolate the minus on the top. We still have that. Let's not spoil our parentheses because we've been carrying the parentheses down. We isolated 3x squared, and what do we get over here? I'm just looking at the numerator over here. We get over here y to the 4 plus x to the 4, and we know we have this common denominator y to the 7th. Now look over here. We're one step away from finishing it, and we're going to finish it. Our final answer will be this minus 3x squared. This y to the 4th plus x to the 4th is represented and equal to a 16. We can just put a 16 over here. This right here represents a 16 because that's what we started with. It's nothing more than resubstituting back. But what's minus 3 times 16? It's a minus 48. Minus 48. You get a minus 48 x squared over y to the 7th, and this right here represents your second order derivative of this function right over here. That right there is your answer, minus 48 x squared over y to the 7th, the second order derivative of this function. So pretty much that's implicit differentiation in a nutshell. I focus more today on polynomial type equations, but you can do this for any kind of equation, and you would only do it really in those cases where you cannot explicitly express y in terms of x. Otherwise, why complicate yourself in a procedure that's more difficult than explicit? Where and when possible, always lean towards explicit differentiation, because this procedure is always 1 or 2 steps away from completion and towards the same final outcome as explicit differentiation. And when you get into second order derivatives, it can become a little more complex than explicit differentiation, which is always easier all the way around. I hope you enjoyed this video. Please stay tuned. We have several more, or actually many more coming. Several more for the differential calculus topics, but many more for the integral calculus topics. Have a good day. Thank you for watching. Bye.